So okay, we are continuing our lesson on assembly directives. So in our previous lesson, we have seen on control directives, and today we will see on data directives. So under the control directives, what are the directives that we have seen? We have seen the if-else, and we have seen the radix. So today we're going to go into data directives. So there are several data directives. So we will start off with set and EQU. Now set has this particular format. It requires a label, and you can actually set that label to a particular expression. Likewise, EQU equals is you can have a label, then equate it to a particular expression. Now, when do we use set and when do we use EQU? Is that for set, you use it to assign a label to an address, whereas EQU you use to define a constant. So I mean you equate it to a value. So let's see an example. So let's say we want to work on a particular addition whereby we want to add the content of hex 10 to the content of hex 20. This is similar to your tutorial 2 question, right? And store the answer at hex 30. So let's say this is the task that we want to do. Are you all able to see? So how do we normally write? Okay, we move any one of these content to working register, and then we add to which file register? 20. Then we can store the answer at working register and we can move it to finally hex 30. This is how usually we write it, right? Now we're going to learn how to do the same program but by using assembly directives. Now take note how is the sequence of things which are being arranged. Always we'll start with include, right? And then we always follow by the program start template, and after program start template immediate is the main program. Is that okay? So now we are in subject. Yes it is. So when it comes to assembly directives, you have to include it just before the program start template. So now we're going to learn how to use the set assembly directive. So whenever you write like this, you write in terms of the data or the file register address. Okay, you as a programmer, you know what is it doing. But if anyone were to look at this, they might be wondering what is at hex 10, what is at hex 20, and why hex 30. So normally, instead of using the address, we can actually use the assembly directive to use a proper label convention and assign them an address. So let's say here you have two values, right? And then this is your result. So what you can do is, these addresses are the same, hex 10, hex 20, and hex 30. What you can do is you can assign a name to these addresses. So let's say the first one is maybe num1 is the name which I want to assign set to which address? Hex 10. Next one, maybe I want to assign number 2. I want to assign it to address hex 20, and maybe the last one, result. I want to assign it to address 30. Oh, sorry. Why just now it didn't turn into purple color is because res is a reserved keyword. So that's why we couldn't use. So when you do this, what happens? You have assigned a name, the label name, to these addresses. So whenever you want to assign, you use set. Are you clear? Because this will be asked in your quiz tomorrow for NP So now instead of writing the address here, you can actually now use the label. Num2, and this will be. So when you look at this, okay, you're moving number 1 to working register, adding with number 2 and storing a result, for example. So do you understand how to use this? So use set to do this. Now let's say, when do we use EQU? So now you're performing addition here, but what about the values that we need to load into these two addresses, hex 10 and hex 20? So let's say at hex 10, remember what a square bracket means? The content of. Some of you got panicked and the test one was asking what does the square bracket mean. So it's okay, but it's all in the learning process. So let's say we want to load the value 33 and into what is the content of hex 20. So we're going to maybe set it to hex 55. Is that okay? So now we need to load these two values, right? So usually how we do, we actually use the literal value. So we're going to move hex 33 into working register, and then we're going to move WF to num1. Are you clear of this? Don't worry about writing and things like that, worry about understanding. And then you have loaded the first value, hex 33, into num1. Then now we need to load the second value, right? So move LW. We're going to move hex 55. Then you're going to move into num2. So here's where you load the value, and here's where you perform the addition. Is that clear? Now here, whenever you see the value, this value, we can also use assembler directive EQU, whereby EQU is used to define a constant. So you can do something like this. Value 1, here you use equals to hex 33, and value 2 is equals to hex what? 55. So instead of writing the numbers here, what do? You just write value 1 and then write value 2. So in this way, it makes your program more readable, right? You know what this stands for, provided that you have given the proper naming conventions here. So are you clear when to use set? When do you use set? Whenever you want to assign a label or a name for an address. When do you use EQU? So define a constant. Is that clear? Any question up to this point? No? Can we move on? Next is the data directives on DB and DW. DB stands for define byte and DW stands for define word. So this db and dw, they are actually used to store values or strings in program memory. So we just learned the assembler directive. So this is actually data directives, to be specific. So one form of data directive is set and EKU. Another form of data directive is this one, data directive to store values or strings in program memory. Now, you can store data or values in program memory. Now, most of the time we only store the program, right? But you can use these data directives to store data and also string. So whenever you store this data and string in program memory, even though you turn off the power, you turn it on back, the data will be there because it is stored in program memory. Now the question arises, why do we want to store data in program memory? Now sometimes, just to give you a very simple basic example, have you seen alarm systems with an LCD display or something like that? Just to give you a rough idea. So even though sometimes when the alarm system LCD, there will be enter the password or something like that. So sometimes there's a power off. Usually they have a backup power. But let's say assume there's no backup power and suddenly the whole system went blank and then the power came on back. You will notice that again the same letters will be there. Please enter password. Right? So that string, just example I'm giving, that string need to be stored in a ROM. So let's say if you store that character, please enter password, those string in the program memory. So each time when you turn it on, the program will extract the strings from the program memory and display it in the LCD. So even though there's a power cut and on back, you will see the same string is appearing there. So I'm just giving a very, very rough kind of idea. There's some data or some strings that you want to store in the program memory. So for example, if you store a password, that password you may want to store in program memory. Right? If you store the password in RAM, as soon as the power is off, you're on back, it's gone. So sometimes there is a need to store certain characters or strings. Maybe you set, let's say you're doing an alarm system using this microcontroller and you set the admin password 123456 by default, which everyone can hack, right? 123456. But let's say assuming you are coming up with a system and there's an admin password 123456. Where do you store this? You can store in ROM, you can store in program memory. So which means it never disappears. It's always there. So let's say as a user, they can set other password, but as an admin, they want to do something, they can actually always type this 123456 and the PIC will check this 123456. Is it the same as the admin password stored in our program memory? If same, okay, then you have the admin privilege to change whatever. You got the idea? What idea I'm giving you is there are sometimes need to store in program memory. That's what I'm trying to convey here. Is that okay? Any questions that you all have? So now, how do we want to store a value in program memory? So that is the data directive that we will be using. So for now, we will learn how to store. In later part in chapter 2, you will learn how to extract them back. So for that, you have to use another pointer, which we'll learn later. So now let us focus on the data directive. So usually this data directive, because we want to store data in program memory, usually where you will write after the entire program. After the entire program, Because after you have written the program, then only there are remaining program memory spaces, right? So the convention is, okay, after you have done with the main program and things like that, then you write here. So what is the data directive? It is DB. DB stands for define byte. And you can store, define byte means you can store 1 byte value. So let's say, for example, I have some values something like this. Is it okay? Now see what happens when I save and you quick build this. Now for this we need to look at program memory. So I'll reduce this back and extend the program memory. So maybe we can put down. This is the data that you see in program memory, right? Are you able to relate this? And make it bigger also. I can make this font big, but not this. So here you can see start. Where is it starting from? What's the address? 1A. Why is it starting from 1A? Why is it starting from 1A? Yes, it is after the RETFIE, right? Where is RETFIE stored? 18 and 19. After 19 is what? 1A. So can you see the red 5 here, which is stored at what? 18? There's another red 5 also at 08, right? Remember this is some directive we'll be learning after this. 08, and then you see go to start is where? At 0. At the 0, RETFIE at 08, and the second RETFIE is 18. So RETFIE, the second one takes up 18 and 19. So the next address is, so at 1A, what you can see? You can see the label. You can see move LW hex 33, right? This hex 33 is because of this L1. Are you able to relate these two? This is very important. That's why I'm asking. Are you able to relate this? So after move LW is what? Move WF. After that is what? Move FW55. After that is what? WF. Do you see, even though I put comment here, is it reflected here? No. What is the next line? Move F, num1. Then the second one, add. And then move WF. And then last one is no operation. Are you following until no operation? And then follows the DB, right? Define byte. Whenever it says define byte, it will store these addresses after this line. So NOP takes up 28 and 29. What is the next address? 2A. Now at 2A, I want you to focus this part at the opcode part, because the opcode is actually showing the content, right? The opcode is actually the content. Do you see this? 1, 1, 2, 2, 3, 3, 4, 4? Are you able to see? Yes or no? So it is storing the first byte 1, 1, and then 2, 2 is stored at the next byte, next address, high address. So 1, 1 is stored in which address? What is the address? 2A. 2, 2 is stored in 2B. 3, 3 2C. And where is 4, 4 stored? 2D. Is that clear? Now, you understood this one, huh? Next one, do you see that there is an assembly language here? ADWFC hex on, but we never write this instruction at all, right? Why is it so? Don't get panic. Now what this assembly part will do is, it will actually refer to this opcode part. Whatever is written in the opcode, if it can translate into any equivalent assembly language, it will translate and display it here. Now in this case, we are not writing assembly instruction. We are saving data. But coincidentally, this 1122, it can be translated into something. So what the assembler does, it translates into something. Likewise with this 4433, it translates into something as well. But our aim here is not to execute this instruction. Our aim is just to store this 11223344. Is that okay? Yes. Very good question, which I wanted to explain after this. Now, Fadi asked a very interesting and important question. Our aim is actually to store data. But since it can be translated into instruction, if you run it, it will execute this instruction. Right? So let's say, clicking here, option F6. I'll show you that when you press F7, you see it going down until NOP. Actually, our main program is only until NOP. But if you press F7 again, it will go down. And it will execute. See, it is something, it executes because of the instructions. So how do we prevent it from not executing? Is we put a stopping loop here. We put a stopping loop. Now how do we put the stopping loop? Okay, we're gonna use an instruction, something like goto, but we call it branch. So branch, let's say put stop label and put it here. So this is to stop the PC from executing So this particular loop, we call it loop, is to stop the PC from executing the data saved in program memory. So when you come this branch is something like goto. So branch, where do you branch it to? To the label stop. Where is the label stop? Here. So it will keep on looping here. So which means it cannot execute the thing down. So let's see. Sorry, 7. So it's going down. So come to this point is, okay, this thing going missing. Why is it automatically branching here? Let's use some other keywords and see. Pause. Pause. Okay, I think I didn't build this now, right? I didn't build this now. So do you see that you get actually stuck here? So it's not, when you do this, you are preventing the PC from going to the data directive and executing it as an instruction. Is that okay? Now you may ask, yes. To store data in program memory. Well, I was just telling all the, not when you're programming, but when you want to save a particular data or a particular string in program memory, which I give the example of, for example, admin password or some character that you want to display, the welcome in your LCD screen, for example. So welcome, please enter your password. That welcome, please enter your password, store it in program memory so that whenever your program starts, it will extract those string from program memory and display it in the 7th segment. So it doesn't disappear. It's always there. Is that okay? Now the next question, if you're not asking, then I know what is the next question going to come. If we put a pause here and the PC is not going down, how do we extract back this information? You will use another pointer which you'll learn later. So that pointer is a similar concept like FSR, but this pointer is for program memory. FSR is for data memory. This particular pointer, the name is table pointer. It is pointer for program memory, specifically to point to data which are stored in program memory. That we will learn later. But for now, how do we store? Is by using DB. Where do we actually put this? Just before the end, data directive end, or in other words, after the main program. Now from the main program, you need to prevent the PC from executing this because in some cases, coincidentally, the data that we want to store translates into somewhat equivalent to some instruction, which we don't intend on executing. Our aim is just to store this value. So we don't want the PC to unnecessarily execute instructions. So we will use these instructions to prevent the PC from executing the data saved in program memory. Is that okay? Any question up to this point? Before we proceed? Now, it's often a good practice to label your values that you're storing in program memory. So, for example, let's say you can give a name array. So, when you put the name array, let's say any quick build, what happens? Do you see the label array here? Where is this label array tagged to? This array is tagged to which data? DB is a assembly directive, is the data directive. This array is tagged to which value? 1, 1. Because the array is tagged to address 2C. What is stored at address 2C? 1, 1. So why is this important for us to actually label it? Whenever you use label, even though in the main program, if we add on some instruction, you will notice that this 1, 1 will no longer be stored in 2C. Do you get the idea? If I add another line here, do you think the 1, 1 will be in 2C? No, it will shift, right? But if I put the label will always follow whatever address that this 1, 1 is stored. Yes. You don't have to label 2, 2. You just need to find out the first element. And then when you can use the table pointer to increment one by one. But if you want to label 2 can, how do you think that's possible? Just put another DB. So when I do like this, there you have it. 2. That is because you just asked, I'm showing you how to do that. You don't have to label everything. You just have to know the starting point only. If you do like what I did just now. Good, that's one of the points which I wanted to mention on DB. It stores every single entry as a single byte. And did you notice something? Like just now when I did something like this, what do you think that happened here? 1 1, then 0 0, and then 2 2 3 3, and then 4 4 0 0. Why does it happen like that? Because every line that you write in the assembly language, it has to start from even address. Why? Why that every line that you write, it has to start with even address? Why? No one want to try? It has to start from even address. Why? Because every single instruction takes 2 locations, even and odd. And the new line always starts at even. Do you understand what I'm saying? Are you following? If you don't understand, just try to understand. So that I'll know what you understand, what you don't understand. One assembly language is 16-bit, right? The first lower byte is stored where? 1C. 1C is even or odd? It's even. It's an even address. 1D is odd. How do you know it's even or odd? Just by looking at the least significant digit. If it's 0, it's even. If it's 1, it is odd number. Are you understanding what I'm saying? If the least significant number is 1, you'll always get number like 3, 5, 7, those kind of odd numbers. I hope you have not forgotten what is odd and even numbers. And if the most significant bit is 0, it will always be 0 for even numbers. Is that okay? So, one assembly language instruction will take up even and 1D is odd. And then the next line starts off back. Do you see what are all these addresses? 6, 8, A, C, E, 10, 2, 4, 6, 8. All these are what? Even addresses, right? Of course, the odd addresses are not seen, but that's why it is jumping by 2. Do you see? Always is the PC is always skipping by 2. And therefore, each line that you write, if you start a new line, the new line will have to start at an even address. So if you write db hex 11, this will store in the lower address, which is 2C. But because you put db in the next line, it has to make the upper, which is 2D, as 00. So you waste some space there. And because you write a new line DB, this new line has to start from the next even address. And that's why it starts from 2E. Is that okay? Am I following? So to prevent such wastages, one of the best practices would be to write the addresses or to save data in even numbers. 2, 4, 6, 8. If you write something like this, let's say, what do you think will happen? Okay, these two will be stored in 2C and 2D. This will be stored in 2E. And then the 4, 4 will be stored in 3, 0. So don't store the answer in odd number. You will end up having extra zeros in between. So always write even. So if you want to write few lines, so either you can write long, all the one line all long, or you can, if you think there's a lot of number, you can just break them up. It is the same thing. If you build this, you'll see that it is the same. The array 1, 1, 2, 2, 3, 3, 4, 4. Oh, sorry, I can write like this, or I can write like how I write earlier, right? 1, 1, 2, 2, 3, 3, 4, 4 in one single line. Why we write two lines like this? Just for the sake of visibility of reading, that's all. Nothing much, but how it stores is the same. Any other question? So this is defined by 4. So you can also use to the famous thing, hello world. You can also use to store string. So when you execute this, when you build this, sorry, you'll see more crazy characters coming up. But it seems like you can't see the hello world anywhere. So for you to see the hello world, you need to go to opcode hex tab, the bottom here. And under this opcode hex tab, there is this one particular column which is for ASCII code. So what this particular column does is, if there are any codes here which corresponds to ASCII code, it will translate that into ASCII character. So therefore you can see here, hello world. So there are 1, 2, 3, 4, 5, 6, 7, 8. Another 8, there are a total of 16 dots here. Why 16 dots? Every dot is for one character. So from 00 to 0F you have how many bytes? 16. One addresses take up 1 byte, right? So from 0 to F is 16. So you can see here, 48 is capital H. This one. 65 is E. 6C is L. 6C is L. 6F is O. 20 is what? Space. Single space. 57 is capital W. 6F is O. 72 is R. 6C is L. And 64 is D. Is that okay? At the same time, you can see some other N, P, O, all the dollar signs. Again, as I mentioned, the ASCII tab translates any ASCII equivalent value. But our concern is only here, right? Hello world. That is actually stored from where? 1, 1, 2, 2, 3, 3, 4, 4, then here onwards. So hex 30 until 6A is where the string hello world is stored. Is that okay? Any question up to this point? We will see how much you understand tomorrow. Next is we'll just finish off this DW part and then we'll take a break. Are you all still here or still sleepy? Sleepy. Still here. Bodily still here. Mind everywhere else. Okay, DW is same like DB. DB stands for defined byte. DW means defined word. Very good. So when do you use DW? Whenever you have one word data or double byte data to store. For example, like this. So you can use defined word. So when you store, when you build this, can you see this value stored as it is? 7654 6754 is one word we have actually used. So you can also use to store single byte value, but what will happen? It will add the 00 in front. Okay, let's say if you do like this. You might be thinking, oh, if I use DW, then I'll store 67 and 56 one shot. But no. See what happens? It takes each entry as one word. So therefore, you can see 67. Do you see? Even though you write here 67, what it'll do, it'll add up 00 in front and make it one word. So the second entry, you add up 00 in front and make it into another word. Is that okay? So most of the time, we only use DW for double byte values. And the same thing, you can use DW for So how do you think the effect between this one and also this one? DB and DW for hello world. Yes? Same. Find out. Yes, it is the same. So definitely for DW and DB, it will be the same. Meaning to say, even though you're using DW, every character will be translated into 1 byte ASCII code. How many bits is ASCII code? 4. Oh my god. 7. 7 bit, right? Why? Have you used the ASCII code table before? It's a 4 bit and 3 bit and try to find what is the character. So every character is packed into 8-bit value. So therefore, even though you're using DB and DW, it doesn't mean that it'll take one and it'll add up 00 and find and make it one word. So if it does that, then the string will be funny. So for the string, the DB and also the DW is the same. It stores the same way. Only for numbers. DB means it'll take every entry as a single byte value. DW means it'll take every entry as a double byte or one word. So with that, we have ended with the data directive. So any question?